We all feel it, don't we? This constant flow forward. Getting older, memories changing, a dropped glass, days shattered. It never just puts itself back together. What's really going on there? Why only one direction for time?
That's a really fundamental question. And the answer, surprisingly, is tied up with this concept called entropy.
Entropy. Okay. Yeah, sounds a bit technical.
It can be, but the basic idea is, well, pretty straightforward, actually. Think of it like this. It's a way to count how many different ways you can arrange the tiny microscopic parts of something, like atoms or molecules, while it still looks the same to us on the big picture level.
Right. So if something has low entropy, that means it's very specific, not many ways to arrange it, like an unbroken glass.
Exactly. Very few arrangements correspond to unbroken glass. It's ordered. Or think about a brand new deck of cards, perfectly sorted. That's low entropy.
And high entropy is the opposite. Loads of possibilities.
Precisely. Like the scattered pieces of that broken glass or a shuffled deck. There are vastly, vastly more ways for things to be disordered or mixed up than ordered. That state is high entropy.
Okay, so for this deep dive, we're going to try and unpack entropy and connect it to why time seems to move just one way. And we're drawing on an interesting article from the Indian Express to help guide us.
That's the plan. And a really good way to visualize this tendency towards disorder is the domino analogy.
Ah, dominoes falling. How does that connect?
Well, picture a perfectly straight line of dominoes, all standing up. That's a very particular, very ordered state, right? Low entropy.
Okay, yeah. Takes effort to set that up.
Right. Now just nudge the first one. What happens?
They all fall down. Chaos.
Exactly. And they end up in a jumbled pile. Now, think about how many different ways that pile could look. Countless ways, really. But there's only one way for them to be perfectly standing in that line.
So it's just much, much more likely they'll end up fallen and messy.
Overwhelmingly more likely. Nature kind of leans towards the messy states because there are just so many more of them available.
That makes sense. And we see this, well, everywhere. The article mentioned a kid's playroom.
Oh, perfect example. A tidy room, every toy in its place, that's specific. Low entropy, but after playtime.
Disaster zone. Toys everywhere.
And that messy state can look a million different ways, right? It doesn't take effort for it to get messy. It takes effort to tidy it up, to force it back into that low entropy state. Disorder is kind of the default path.
I can confirm that from personal experience. And what about cream and coffee? That was another one.
Yeah, think about it. You pour cream in, you get those nice swirls for a second. That's relatively ordered, separate. But almost instantly it just mixes. And you get that uniform light brown color. You're never going to see it spontaneously unmix, separating back into black coffee and white cream.
No, definitely not.
Because the number of ways the coffee and cream molecules can be mixed together is astronomically larger than the number of ways they can be separate. It's the same reason ice melts or perfume spreads out systems naturally move towards the states with the most possible arrangements, which are usually the mixed up, dispersed ones.
So this isn't just like a tendency, it's tied to physics. The article brought up the second law of thermodynamics.
Absolutely critical point. Back in the 1800s, people working on steam engines noticed something fundamental about heat. It always, always flows from hot things to cold things on its own.
Right, like a hot cup cooling down.
Exactly, never the other way around spontaneously. A physicist named Rudolf Clausius formalized this observation, that's the second law, and he realized this directionality of heat flow seemed deeply linked to the direction of time itself. It was one of the first big clues.
Interesting. So the way heat moves gave a hint about time zero.
It did. But the real aha moment, the why, came later with Ludwig Boltzmann. He was an Austrian physicist who looked at it statistically.
Statistically? How did that change things?
Boltzmann realized the second law isn't an absolute rule that individual molecules must obey, like gravity. Instead, it's about probability. Immense probability.
Probability, okay. Like the dominoes again.
Precisely. He argued that disordered states are just vastly more numerous, vastly more probable than ordered states. Remember the shuffled deck of cards the article mentioned?
Yeah, the number was mind-boggling. 8 times 10 to the 67.
Something like that. An insane number of possible shuffled orders. But how many ways can the deck be perfectly sorted, ace to king, by suit?
Only one way.
Exactly. So if you shuffle randomly, what are the chances you'll hit that one perfectly ordered state? Practically zero.
Vanishingly small. So Boltzmann applied that thinking to molecules.
Yes. He said systems naturally explore all their possible configurations, and because there are just overwhelmingly more ways for the molecules to be in a disordered state, like mixed coffee or fallen dominoes or scattered heat, that's almost certainly where you'll find them. This statistical tendency is the second law, and it's what gives time its direction.
Okay, so that leads to his famous equation, S equals K L N W. It looks intimidating.
It does, but the core idea is captured in the WO. W stands for the number of those microscopic arrangements, those different ways the tiny parts can be configured that all look the same macroscopically.
The number of ways. Okay.
Right. And the S is entropy. The equation basically says entropy is higher when there are more ways, a bigger W, for something to be arranged. Low entropy states, like the tidy room, have a small w. High entropy states, the messy room or the mixed coffee, have an enormous W.
So things just naturally drift towards states with a higher W, higher entropy, because there are simply more paths leading there. It's a numbers game.
Exactly. It's statistical inevitability. Think about spilled milk, another example from the piece.
Oh, yeah. Always a tragedy.
Once it's spilled and spread out, maybe mixed with cereal, the milk molecules are scattered in countless positions. For them to all spontaneously jump back into the carton, perfectly reversing their paths,
It's not going to happen.
the odds are just astronomically against it. It's not forbidden by basic physics laws, just statistically impossible in reality.
And something like aging, how does entropy fit there?
Well, you can think of aging as the slow accumulation of random changes and, well, damage at the cellular level. Tiny errors, molecules getting bent out of shape, things not being repaired perfectly.
A gradual increase in disorder within our bodies.
In a sense, yes. To reverse aging, to become younger, every single one of those accumulated changes across trillions of cells would need to spontaneously undo itself, returning to a previous, more ordered state. Again, the statistics are just overwhelmingly against it.
Makes sense. And this even applies to technology, like engines.
Absolutely.
Sure.
An engine burns fuel to do work, but it always produces waste heat.
Right.
That heat isn't lost energy, it's energy that's been spread out into the random jiggling of air molecules.
Increasing the disorder of the surroundings.
Precisely. Trying to perfectly gather all that random jiggling back into useful work is, again, statistically futile. Refrigerators seem to defy it by making things colder, reducing entropy inside.
But they don't really break the rule.
No, because they use energy, and in the process, they pump out even more heat into the kitchen, increasing the total entropy of the room plus the fridge contents. You always end up with more overall disorder.
It's really woven into everything. And understanding it actually matters, practically speaking.
Oh, definitely. Engineers constantly battle entropy to make engines more efficient, trying to minimize that wasted heat. Designing cooling systems for computers, managing data centers, that's all about managing entropy and heat flow.
And in medicine, too.
Yeah, understanding how cells break down, the processes behind aging or diseases, these often involve entropic effects at the molecular level. Understanding it could lead to, well, new ways to intervene.
And this isn't just an earthbound thing, is it? It's cosmic.
Very much so. The standard picture is that the universe started in an incredibly low entropy state at the Big Bang, extremely hot, dense, and uniform, highly ordered in a cosmological sense.
And since then?
Entropy has been increasing. Gravity pulls matter together, forming stars and galaxies that actually increases entropy overall. Stars burn fuel, radiating heat and light, increasing disorder. Even black holes, which seem like ultimate order, turn out to have enormous entropy related to their surface area. It's a universe seemingly marching towards greater and greater disorder.
Wow. So from my coffee cooling down to the evolution of the entire universe, it's all driven by this tendency towards more possible arrangements.
That's the essence of it. So when toast burns or perfume fades, or you just feel that instinct to tidy up a mess, you're experiencing the second law in action. The arrow of time isn't some external force pushing us forward. It's the universe playing the odds. And the odds overwhelmingly favor states with more disorder, more entropy.
So to wrap it up, time's arrow isn't really a force, but more like a statistical trend. It flows one way because the microscopic arrangements that correspond to later are just vastly more numerous and probable than the arrangements corresponding to earlier.
That's a great way to put it. It's a consequence of probability applied to countless particles.
And the implication, if states are always moving towards higher probability, higher entropy states, it means the exact configuration of everything right now is unique. It won't happen again.
Exactly. That specific arrangement of atoms making up you, me, this room, the planet,
Mm.
It's fleeting. The constant increase in entropy ensures that each moment is genuinely unrepeatable.
Which leads to a pretty profound thought for everyone listening. If every moment is truly unique and gone forever once passed, how does that influence the choices we make, the things we prioritize?
A very important question to reflect on.
And specifically for you listeners who might be preparing for the UPSC exams, grasping a fundamental concept like entropy is, well, surprisingly useful. It's not just physics. It's a lens for thinking about efficiency, resource management, environmental degradation, even social systems. Why do things tend towards disorder unless energy is put in?
Absolutely. Understanding these deep principles helps you connect dots across different subjects, seeing how order emerges, how it's maintained, and how things naturally degrade or disperse. That's a powerful analytical tool.
We really hope this deep dive has shed some light on why time flows the way it does, all thanks to entropy. If you found this useful, or if it sparked more questions, please do like this session, subscribe for more, and leave your thoughts or queries in the comments below.
We'd love to hear from you. And remember, our discussion today was inspired by an insightful article on this topic in the Indian Express.